All right, here's Joshua.
So hi everybody, and that was a fantastic talk and leads right very nicely into mine. So I want to talk about how we go for the win, how we make open source hardware the standard for scientific research from now on rather than sort of an anomaly that might be happening in a couple labs. So open source hardware for scientists works more or less the same way it does for everybody else, only the numbers are bigger. So $1 million sounds like a lot of money to basically everybody, but if I'm looking at it from my research budget perspective, that pays for 2 students. So I can get 2 PhD students through for $1 million. Why does it cost so much? Part of it is overhead. We spend over 50% of the money that comes to say, our university on overhead costs that we can't get rid of. And then there's also the cost of the equipment. Everything that you buy as a scientist, it is as if it was plated in gold, and that's what we're used to paying. And so if you take the open source hardware approach, though, even if you're producing something relatively simple, if you share it, and put a viral license associated with it, like a share-alike license, it will come back to you, and it'll come back to you in a big way. So that cartoon actually happened in real life. People shared basic little test tubes, and then others build off of it. So we had centrifuges. Well, centrifuges normally cost, at the bottom scale, a few $100s. The good ones, like the ultra centrifuges, are a few $1,000s. And now you can take the Dremel that you already have in your tool chest, print out like a 10 cents worth of plastic, and make the Dremel fuge. The magnetic test tube racks are over $500 a piece. So you can justify the cost of, say, buying a TAS if you know you have to print 4 of them. All of a sudden, you have the ability to make just as good of magnetic test tube racks as you buy commercially, the proprietary ones, but now you can make them the open source variety. So this picture really summarizes how my lab now thinks about doing research. We used to be a photovoltaic lab, or primarily a photovoltaic lab, so we do a lot of optoelectronic testing equipment. And one of the tools that we had was a filter wheel changer. It was automated, and all it does is rotate around and put a different colored filter in front of a light path so we can test it for solar cells. And mine broke. It was $2,500 to replace and it had a 5-month lead time. And why is it so expensive for something so simple? Well, hardly anybody in the world needs them. It's a very specialized piece of equipment. They don't have them sitting on the shelves at Walmart. It's something that they have to make specifically for us. So instead of buying one, I hired this high school student to use a discarded computer from the university that we put Debian on. He put OpenSCAD on it. OpenSCAD is a script-based CAD package. And so not only did he fix my automated filter wheel problem, he fixed all automated filter wheel problems for all of time. So it's parametric. So if you want, say, 4 filters or 10 filters, you just plug in 4 or 10. It immediately spits out the code. If you want to go from, say, a square filter to a circular filter, the same thing. It's running on Arduino. It uses the stepper motors that we had left over from the RepRaps. And you can see this is one of the older versions of RepRap, so this is a little bit dated now. It's something that you can basically completely produce with off-the-shelf electronics that you, say, buy from SparkFun, leftover M3 nuts and bolts that you have from your RepRap, and the RepRap itself. So that system is better than anything that you could buy on the market. It's not proprietary, and it saved me over $2,000. Now, of course, the open source hardware movement, if you're not familiar with the RepRap project, you really should be. At Michigan Tech, we have a class called Open Source 3D Printing where everybody has to build one in order to even get the first 10% on their grade. And so this is the first class of happy students, all building their own equipment. And then we spend the rest of the semester developing their skills as kind of hacker makers, specifically to go after high-end scientific equipment. So this class last year went through 100 different projects of things that would be useful to scientists every day. So here's some examples. When we do this, we try not to just solve a problem, we try to solve all the problems. So a lot of our projects are basically creating libraries of things that other scientists need. So optics labs, one of the major expenses is the mechanical fixtures, all of which are easily printable with one of these low-end 3D printers. Something like a mirror mount will cost $50. And you can print that out in, say, 10 cents worth of plastic, and you can start to make more and more sophisticated things. What we found when we looked at the entire optics library is that you save between 97 and 99% of what you would be otherwise wasting on kind of proprietary black box equipment. Then once you put an electronics package on it, you can get more and more sophisticated very quickly. So on the left-hand side, you see a student working with an open source colorimeter. And what we did is we took open source plans for a teaching-based colorimeter, and we kind of amped it up to the point where you could use it for real scientific research. Then one of our funders also wanted a nephelometer to do turbidity measurements to test water in the developing world. We added like 5 cents worth of electronics, and now we have a handheld device for under $100 that can do both nephelometry and colorimetry. Both of those techniques alone cost over $2,000. And so you can build one of these yourselves for about $100, and you're saving $4,000 in equipment costs. But then we went a little farther. So NECI and nitrate.com folks that make enzymes to do nitrate testing for things like farms, for water testing, liked the idea, only they wanted something a little bit more handheld, a little bit more, say, modern looking. And so we made this. So this is a stripped down version. It's still using the same chips as in the Arduino, but we've got rid of the Arduino platform. It communicates with any Android device, your cell phone, laptop, tablet, and it can do everything that you would do. You would normally spend hundreds of dollars for a nitrate testing in a commercial, professional lab. You can do sort of in your garden. And that's where all of this is heading, is it's not just taking down the costs for professional scientists, it's also opening it up to the rest of the world. So they can do things like you could build an ultrascope. You could think about actually doing that with your kids and tracking interstellar objects at home. Like, that's amazing. And if we're going to encourage people to join the STEM fields, it's much more exciting to do real science than it is to do kind of cookie cutter stuff that's in the back of a textbook. But we can go further. One of the most common scientific instruments in, say, a lot of chemistry labs, biological labs, is a syringe pump. Syringe pumps on the low end cost a few $100s. On the high end, for something like this double syringe pump, is a couple $1,000s. And so we, again, using that sort of same rep-rap tradition, where we're using parts that we'd have off of 3D printers, 3D printed parts themselves, and a Raspberry Pi to run the whole thing, have made a web-enabled completely automated syringe pump. Now, this isn't just a syringe pump that we found useful for our lab, and we were using it for 3D printing, but it can be used for everything. So we've solved all of syringe pump problems for all the rest of time. You can go into the code, you change, say, this type of syringe that you want, you change the motor, and you immediately, all the pieces reconfigure so that they're easily 3D printable, and you can make a syringe pump for your needs. And so these are being used by thousands of people all over the world. People have hacked it and taken it back to go work on an Arduino. This is the future of science, where we all put in a little bit and we stand on the shoulders of the giants that came before us. So what does this look like, though, from a funder's perspective? Today, tens of millions of dollars are being wasted by people that are trying to push science forward on proprietary equipment. So let's look at the syringe pump just as an example. If we look at the savings that you have for printing one out and making it yourself at home, you save between $153 on the lowest cost, cheapest piece of garbage that they put out in China, to over $2,400 for something that's good that you'd actually put in a lab. In the first couple months that we put our syringe pump designs online, it had already been downloaded 1,000 times. And let's say what that means is we assume that most of them are being downloaded and used by scientific labs. The downloaded substitution value is between $168,000 and $2.5 million, and that was only after the first couple months. Let's assume it cost us $30,000 to develop them, and we had a 52% overhead. What that means from the scientific funder's perspective is they're making a return on investment of over 750,000% for sure, and it's probably closer to over 12,000%. And realize that's just the first couple months, and that doesn't include anybody building off the ideas and making them better and using them for more sophisticated equipment. And so now science funders have an option. They can follow the standard model. And so I'm talking to people like the National Science Foundation and the NIH. And in the standard model, we all write grant proposals, and our chances of winning that grant is 10%. And if you ever want to destroy your soul, write some grant proposals. So you put all your blood and sweat and tears and money and hard work into trying to make something good, and 1 out of 10 good scientists is going to win the grant. That scientist normally has white hair and has been around for a little while, and he's happy. So in the standard model, we're going to spend $100 million, or $1 million. $100,000 in the first year goes to that scientist. The 9 other scientists, the 9 out of 10 of other scientists are unhappy. They don't get anything for all their work and realize that they were spending their time and effort writing those proposals. In the open source hardware model, the same thing happens. But instead of buying equipment, you're buying the design. You're saying, I'm going to pay you $100,000 to make whatever the tool it happens to be. So again, one person's happy, and the rest walk away unhappy. But where things start to get interesting is in year 2 through 10. So in year 2, in the proprietary model, again, only 1 scientist is funded. But in the open source hardware model, because we know we can knock the cost down by at least a factor of 10, all the scientists are funded. All the scientists get the best equipment that's available on the market now. And you're paying them to push it further, to take the tools that they have because they're open and go to the next step. And so if you look at the little stars on all the little golden boxes on the right-hand side, those are open source hardware devices that have been improved by people that got grant money in order to push it forward. While on the proprietary model, you're only still 1 scientist out of 10 is being funded every year. If we add it all up, after 10 years, only 10 scientists have been funded using how we currently fund science. 90 scientists are unfunded, and of the ones that were funded, most of their tools are out of date because we know technology is moving pretty rapidly now. We look at the open source hardware model, 91% of the scientists are funded. You have 91 state-of-the-art pieces of equipment that's easily upgradable. All the plans are open. If you need a software upgrade, you just download it and go. And that gives you a return on investment of over 800,000%. Now that's a real number. You're going to make real money from a scientific perspective if we start pushing open source hardware everywhere and we fund its development. So we need a couple policy changes in order to encourage this. And so on the national level, we need a task force to identify the strategic goals where we know we're spending millions of dollars on this particular type of hardware. It's a ripe, kind of low-hanging fruit to pick in order to turn it into open hardware. That's where our money should first go. We start having to have specific calls for federal funding for open hardware, just not calls to make scientific equipment, but to go the next step and ensure that the documentation is done so that all the rest of us can replicate it. We need a free online catalog of validated scientific hardware. So from a scientist's perspective, it's just not cool that, say, a hacker collective in Europe made something really neat. I need to be sure that if I'm going to put serious money into it, that it's going to work in my lab and it's going to work as soon as we follow the instructions exactly. So it needs to be validated. The NIH already has a 3D printing repository, which some of you might have seen, but the coolest thing about it is they have an open source hardware part to it. And so this idea is already beginning to percolate the major funders in the US. We need a purchasing policy preference for open source hardware for all government-funded projects. And I know if there's any other scientists in this lab or in this room, I guarantee you back at your lab, there's pieces of proprietary equipment sitting unused. They get mothballed quickly. It's because a company went out of business, they lost some of their key staff, then maybe they upgraded to a new version and they don't support yours anymore. That can't happen anymore. That's just wasted money. It's money that's sitting on the table. But if it was open source hardware, you could always go back in and at least use the components. You could at least move it to the next stage. We need to start encouraging people to create their own equipment. And so that means a makerspace at every public university that doesn't have one already, and at least a RepRap 3D printer in every school. Because a lot of the lowest hanging fruit can actually be mostly 3D printed and with a couple of electronic components that you can pick up off the web. If that starts to happen, we're going to see more and more students interested in the STEM field because they get to do real science. And I can tell you as a scientist, there's nothing more fun than discovering something new for the first time. And there's no reason that we shouldn't be allowing our students to do that with the best scientific tools available anywhere. So I thank you very much for your time and attention. Everything that my lab does is free and open and available to everybody. We tell you what we're going to do ahead of time. We publish all of our code, all of our designs. And I know there's a couple other good scientific hackers in the audience. If I haven't highlighted your work on Appropedia and the open source lab, please either send me an email or post it there yourself. We'd love to share your good work to everybody else. Thank you.